of lagging of flux density behind the magnetizing force in a ferromagnetic material subjected to cycles of magnetization is known as hysteresis.
To draw a hysteresis loop, let us consider a soft iron cored toroid carrying current I. If N is the total number of turns per unit length, then magnetizing force H is equal to mu naught N I. The value of H can be changed by varying current in the coil. You can see that when the iron cored toroid is subjected to a cycle of magnetization, the resultant BH curve traces a loop called hysteresis loop.
The term hysteresis is derived from a Greek word hysterein, which means deficiency or lagging behind. If a piece of ferromagnetic material, for example iron, is subjected to one cycle of magnetization, the resultant BH curve or IH curve is a closed hysteresis loop ABCDEFA called hysteresis loop or a hysteresis curve. It can be noticed that B or I always lags behind H. Thus, at point B, H is 0, but flux density B has a finite positive value OB. Similarly, at point E, H is 0, but flux density B has a finite negative value OE. In the beginning, let the toroid be unmagnetized and the situation be represented by point O. If now H is gradually increased by increasing current in the toroid, B is found to increase along the curve OA and reach a point where further increase in H shows no further change in flux density B. This shows the saturation value at A. All domains are aligned at this stage. If now H is gradually reduced by decreasing current in the toroid, it is found that curve follows the path AB instead of AO. However, at point B, magnetizing force H becomes 0, but flux density in the material does not reduce to 0, rather has a value equal to OB. Thus, some magnetism is left in the specimen, which is called residual flux density. It is also called reminiscence or retentivity or residual magnetism. I want you to note that B lags behind H. This effect is called hysteresis. Now, in order to reduce the residual flux density or retentivity in the material to 0, it is necessary to apply H in the reverse direction. This can be done by reversing the current in the toroid. When H is gradually increased in the reverse direction, the curve follows the path BC. However, at point C, B becomes 0, but H has some negative value equal to OC. This value of H needed to eliminate residual magnetism is called coercive force or coercivity. All domains do not remain aligned at this stage, and hence their net dipole moment becomes 0. Now, H is further increased in the reverse direction until the sample reaches its saturation value in this condition. Here, D is the point denoting that the sample has reached its saturated value. If H is now further reduced to 0, point E is obtained and the sample again retains some magnetic flux density. The remaining part of the loop can be obtained by increasing current to produce H in the original direction. Here, the curve ABCDEFA is called the hysteresis loop. In general, the value of the magnetic intensity of a material when the magnetizing field is reduced to zero is called retentivity of the material, whereas the value of the magnetizing field required to reduce the retentivity to zero is called coercivity of the material.